As we have finished about the induction motor, introduction of the induction motor, and we have learned the output equation of the induction motor, and we have learned the stator design of the induction motor. We will see some basic problems on this induction motor. So first set I have already given to you. This is second set. So the first question is that determine the main dimensions, number of radial ventilating ducts, number of stator slots, and the number of turns per phase of a 3.7 kilowatt 400 volt 3 phase 4 pole squirrel gauge induction motor to be started by a star delta starter. Work out of the winding details. So what he had been asked here, the main dimensions. So the main dimensions means D and L. D means my diameter of the core, L means length of the core, and the number of radial ventilating ducts. How many the ventilating ducts will be there? Yes. How many the ventilating ducts are there? So that we need to study. Then how many stator slots and the number of turns per phase. Per phase, how many turns? Here the phase power had been given 3.7 kilowatt. Voltage is 400 volt and it is a three phase. The number of poles is 4 pole. The frequency is 50 hertz. He had been given squirrel gauge induction motor. So usually according to the construction of an induction motor, so there are two types of the induction motor will be there. One is slip ring induction motor and one more is squirrel gauge induction motor. You have studied the basic difference between squirrel gauge induction motor and slip ring induction motor. And here it has to be started by a star delta starters. We have different starters like dual starter, auto transformer starter and star delta starter. Here they have been used star delta starter. So some values they had been given. Average flux density, yes. Average flux density in the gap, it is 0.45 Weber per meter square. Average flux density in the gap means there is a gap between the rotor and stator. In that there is a magnetic flux. So that magnetic flux density had been given 0.45 Weber per meter square. Then ampere conductors per meter, he had been given 23,000. The value of this usually lies in the range of 20,000 to 35,000. And efficiency it is 0.85 and power factor it is 0.84. Choose the dimension to give a cheap design. So he had been asked that to give a to design the main dimension with a cheap design. So I will tell you. This is not one. Yes. To obtain a cheap design, see here, to obtain a minimum overall cost, it should be in the lies of, it should be range in the 1.5 to 2. So that had been given. Cheap design means it is a minimum cost. So Q is my output power, V is 400 volt, number of phases 3 and number of poles 4. This had been given. 50 hertz. My average flux density it is 0.45. My specific electric loading is 23,000 and efficiency 85%, power factor 0.84 and this is window factor that is 0.955. Now, what is the main dimension what we need to find in this question? you need to find main dimension D and L. We need to find ventilating ducts. We need to find number of stator slots. Then we know the output equation of an induction motor Q equals to C naught D square L Ns, where is C naught means output coefficient. So output coefficient is being given as 11 BAV AC into kW into efficiency into cos phi into 10 raised to minus 3. So this in some books what they will be giving, please uh, switch off your mics. So in some books what they will be giving, it is just they won't consider the efficiency. So efficiency will consider later and that will be not good method. So directly for the time saving you just do this only. So Q equals to 11 BAV into AC into kW. kW means my window factor into efficiency into cos phi into 10 raised to minus 3. And we don't know what is D square and what is D and L. We need to find these both terms and D and L we should find out. Now, so applying all the values in C naught, we will get 11 into 0.45 into 23,000 into 0.95. So all this value you will get it is at 77.63. Yes, this I will get as yes, this I will get as 77.63 by applying all. Now, what is how we will convert your RPM into RPS? Just divide by 60. Now, here NS, we know the formula for NS equals to 120F by P. So, NS equals to 120F by P means what will become NS? So, 2F by P. So, 2 into 50 by 4, 4 had been given number of poles, it is 25 RPS. Now, in this equation, what I had have? I know the Q, I know the C naught, I know the NS. Now, I should find out the product of D square L. So, D square L by simplification, what we will get? D square L you will get Q by C naught into NS. So after this you will get, after applying all the values you will get this value. So D square L equals to 1.9 into 10 raised to minus 3 meters. Now in a question he had been given for a cheap design. Cheap design means it should be a minimum cost. So for a minimum cost the ratio L means my length of the core to the pole pitch, it is 1.5. As we have learned this 1.5 to 2 this. So I can take this is I am taking, you can take 1.6, 1.7 till 2 you can take, but I am taking as 1.5. Now, yes. Now L, what is my pole pitch? Pi, this lambda equals to pi d by P. L equals to, instead of pi lambda, I will use pi d by P. So it is equals to 1.5. So after all that, you will get L by, after all simplification of this, you just transfer to denominator to LHS to RHS. Then you will get L by D equals to 1.5 into pi by P. So 1.5 into pi, so divide by 4. So you will get 1.178. So now L by D equals to 1.178. Now L equals to, if I shift this to here, L equals to 1.178 D. Now place instead of L, now place instead of L in this, you place here. Now you will get what you will get? D square into 1.178 D. So you will get this. So finally you will get dq equals to 1.9 into 10 raised to minus 3, 1 divided by 1.78. So you will get finally D equals to 0.117. So it is 0.12 meter. And L equals to 1.91 into 10 raised to minus 3. So after simplification, you will get L equals to 0.13 meter. Now you get the main dimensions is finished, D and L. Yes. If you have any question in between this, please raise your hand. Now pole pitch. So what is the pole pitch? Pi d by P. So 0.12 into pi by 4. So you will get 0.094 meter. So the length of the core and therefore one radial duct is 10 mm. We will consider one radial duct is a 10 mm wide is provided. So net iron length. So Li. So we will use net iron length. This is my stacking factor 0.9. So my total length is 0.13 minus my radial duct. For 10 mm wide, I will use one radial duct. So you will get net iron length is 0.108. So now how many radial ducts? So almost it is 0.10. It is my length is 0.13 meters. So I will use radial duct as a for 10 mm. So this divided by this, you will get the radial. So almost 10.8 radial ducts you will get. Or you will use about, you will get net iron area length 0.108. Next, turns per phase. So turns per phase basically P5 equals to BAV pi dl. For any basic flux per pole, we will give it is an BAV into pi dl by P. So this if usually this P is transferred to RHS, then it becomes denominator. So 0.45 this you will get after applying all BAV is given in the question 0.45, D you have find out 0.12 and L you have find out 0.13 divided by 4. So now 5.5 into 10 raised to minus 3 Webers. So as the machine is started by star delta starter. So it is designed for delta connection. So star delta starter means my secondary side or my motor is connected to delta. In delta, my line voltage and phase voltages are same. So stator voltage per phase equals to 400 volt. Now stator turns per phase TS equals to ES by 4. This is number of turns per phase. My voltage is 400 as we done in the transformer the same. So 4.44 F into 5M into kW. So you will get 343 turns. So this is not final still. So right now you will getting stator turns per phase. It is 343. Now we will revise that. Number of slots. Usually the number of slots will be selected as the slot pitch should be lies between 15 mm to 25 mm. What is slot pitch means? It is number of stator slots per pole. So I am taking it is a slot per pole per phase. QS I will mention it is 3. In some books it will be given as 4, 4.5. If it is a round figure, I will treat it is an integer slot winding. If it is in 0.5 or in decimal, I will take it is a fractional slot winding. But many of the problems we will consider it is an integer slot winding only. So now total number of stator slots. I consider it is number of taking slot per pole per phase is 3. So now how many stator slots I require? So I will consider 3 as my slots per pole per phase and 3 is my number of phases and what is this 4? It is number of poles. So 3 into 4 into 3 you will get 36. Now we'll see stator slot pitch. Stator slot pitch is pi d by number of stator slots. So stator slot pitch pi d by SS. SS I will mention it is a slot pitch. Sorry, not SS means it is number of slots, stator slots. So pi into 0.12 divided by 36, it is, you will get 0.01047. That means it is in meter. Now convert it into millimeter, you will get 10.47 millimeter. So here in this problem they had been taken the slot pitch in between the 10 mm to 30 mm. So here the slot pitch is within the limits. So this number of slots is acceptable. 36 is acceptable. If my slot pitch below 10 mm or above 30 mm, then it is not acceptable. Then you need to take here 4. Now it is in the range 10 mm to 30 mm. In general, your textbook, in textbook, it had been taken 10 mm to 30 mm. In general, we will take it is 15 mm to 25 mm. Now, the slot loading. So, slot loading is, in some questions, they will be given slot loading should not cross 750 ampere conductor or 800 ampere conductor. So at that time we will check this value. Right now this is not required for this. In some questions they will specifically give that, further I will solve. Now, so total number of stator conductors. So total number of stator conductors 6 into TS. So why I have taken 6 here means because one turn consists of two conductors. So now Z by 2 equals to T equals to my Z by 2. Now Z equals to 2T, right? So for a phase I require one turn consists of two conductors. Now then why it is multiplied by 3? 3 means it is number of phases. So that means 2 into 3. 3 is my number of phases and 2 is my one turn consists of two conductors, or two conductors compose one turn. Now, so total 2058 conductors. Now, how many conductors per slot that? So total 2058 conductors. So divided by 36. So it is 57 slots will be there. 57 slots. Now we will see actual number of turns per phase. So actual number of turns per phase means how I would calculate my number of conductors. It is number of slots who had been joined. Yes. Number of turns per phase means, so each slot contains 36 conductors. So 36 into 57. So divided by 6. So 342 conductors. Now initially it is 343. Now after revision we will get it is 342 conductors. Now coming to the winding details. So single layer mesh winding placed in semi-closed enclosed slots is used. What is mesh winding means? Usually this will be used for low voltage machines. Yes, this is my mesh winding. Usually one large conductor will be one small conductor. However, you learn in lap winding and wave winding. But in lap winding and wave winding, what will happen? All the conductors will be of the same size. But here one large conductor and one small conductors will be there. And it is full pitch. In between that there is a 180 degree. And usually it will be used for AC machines. So this is of my mush winding. See this is smaller conductor and this is connected to larger conductor. One large conductor and one small conductor will be connected here. Yes. No. Number of coils had 36 coils. So divide by 2 make it per this, and number of coil per phase. So number of coil per phase means it is there are 3 phases, 18 by 3 it is 6. So as there are 3 slots per pole per phase, so or you can consider 9 slots per pole per phase. If the coil span is 9 slots, coil side is slot 1 is connected to coil side 9. However, you done in the lap winding 1 plus 9 10, 2 plus 9 11, 3 plus 9 12, the same thing he had been done here. Here. See 1 plus 9 is connected, 1 is connected to 10, 2 is connected, 2 plus 9 again it is connected to 11, like that. Now, the second question is same thing. Obtain the following design information for the stator of 30 kilowatt, 440 volt, 3 phase, 6 pole, 50 hertz, delta connected squirrel gauge induction motor. Main dimension of the stator, number of turns per phase, number of stator slots, number of conductor per slot. Assume suitable value for the missing design data. Just he had been given like this only. So whatever the missing data had been, you need to assume. This missing data will be available into either it will be available in handbook of electrical machine design, or in textbook we had been given. Anyway, as the classes will start, I will show this missing data handbook. But 99% as we will set the question, as we are setting the question papers, so we will give the all data. As we will give the all data. Now here what various missing data are assumed for from referring to design data handbooks or table in textbook. So this when the classes will start, I will show this handbook. But right now they have been assumed the flux density is 0.48. This is 20 electric loading, specific electric loading is 26,000, efficiency 88%, cos phi is 0.86, and your window factor is 0.955. So here it is the main dimensions. So the same thing, however we solved for the previous problem with applying the formula. So you will get the C naught as 99.2 and NS you will get 2F by P. So 2 into 50 by 6, so it is 16.66 RPS. So by the product of D square L, they had been given 0.0182 after finding. So 30 is 30 kilowatt he had been given in the question. Now this also one thing you need to see, designing the machine for the best power factor. So I am designing the machine for the best power factor. So this he had been given. Yes, you can see. So power factor plays a very important role in performance of induction motor. Hence, to obtain the best power factor, the following relation will be used for separation. So pole pitch by core length is equals to 0.18 by pole pitch. So what is pole pitch now? My pi d by p. So by pi d by p divided by L equals to 0.18. So D you will get D equals to 0.135 P root L. So this is for the best power factor. Yes. So for the best power factor, I have assumed in the question you will be given. So for the best power factor, it is 0.135 P into root L. So solving D and L, you will get finally D equals to 0.33 meter and L equals to 0.17 meter. That you can do. It's a basic mathematics. So number of stator turns. So if I want to number of stator turns, I require the flux. So flux equals to BAV into pi dl by P. So you will get the flux as 0.141 Webers. Assuming since it is a delta connected system, my E phase voltage and VP terminal voltage and this phase voltage will be the same generated voltage. So since it is connected in delta connected system, line voltages and phase voltages are same. So TPH equals to EPH turn per phase, it is 148. So the number of stator slots I had taken 3. Here again they have been taken 3. So total number of slots is 3 into number of 3 into 3 into 6, where 3 is Q and 3 is my number of phases and 6 is my number of poles. So 3 into 3 into 6 you will get 54. So total number, now we need to find number of conductor per slot. So total number of conductor equals to 148 into 2 equals to 296. Now number of conductor per slot. So total conductors it is 296. So divided by, so number of conductor per slot. For one slot, how many conductors will require? So it is approximately 5.5 has been chosen, assuming 76 conductor per slot. Now it is 54. Now consider 76 conductors per slot. So total number of conductors it is 54 into 6. So it is not 76, it is 54 only. So it is 54 only. So total number of conductors is 54 into 6. So it is 324 conductors. So revised number of turns per phase it is 162. 324 by 2. Then coming to the same problem, find the main dimensions of 15 kilowatt 3 phase 400 volt 50 Hz 2810 rpm squirrel gauge induction motor. Efficiency of 88%, full load power factor 9.9, specific magnetic load is 0.5 Weber per meter square, specific electric loading it is 25,000 ampere per meter, that is ampere conductor per meter. Take the rotor peripheral speed approximately 20 meter per second. So he had been given my output is 15 kilowatts, phases is 3, voltage is 400 volt. So efficiency, all the values here had been given. So with the help of the formula, find out the C naught output coefficient. And here the speed of the rotor at full load is 2810 rpm. And the nearest speed curve, how you will find the synchronous speed usually? How you will find out speed? So ns equals to 120 f by p. So now if f is a 50 hertz, if f is a 50 hertz and p is a 2, then you will get my synchronous speed is 1500 rpm. The same thing he had been given. So the nearest speed is 3000 rpm. You will not get 2900, 2500, you will not get. So I will see. No. If frequency is 50, if my pole is, if f equals to 50 and my p equals to 4, then your answer will be 1500 RPM. 1500 RPM. In the same way, if F equals to 50, if X equals to 50, P equals to 2, I will get 3000 RPM. So you cannot get like 2800, 2100, P will be always in even numbers. So they had been chosen like this. So 3000 by 60. So the nearest synchronous speed is 3000. So I convert it into RPS. So it is divided by 60. So 50 RPS. So with the help of that, you have find out d square L equals to the product of d square L equals to 2.88 into 10 raised to minus 3 meter cube. Then the why it is meter cube, d into d it is meter square into L is meter, so it is meter cube. Then the peripheral speed v equals to pi d ns. So v, whereas v is velocity, v equals to pi d ns they had been given. So with ns I know this speed in RPS, pi I know, v had been given 20 meter per second. So from this equation I can find out d. So from if you know the d, then applying this value here, you will get L. This is of basic mathematics. So L equals to 0.177 meter. So in next class, I will solve some more problems. So again, 3 or 4 problems will be there. Regarding the stator slot pitch, I will teach in next class. 1 minute.